Okay, last one, section 9.2. So, wrong one. There we go. So the big thing we're doing now, which will help you with that last assignment, is now we're doing two samples and we're going to do two means. So this is section 9.2. Don't have time to do the entire chapter, so I picked this section. So we're looking at two means of independent samples. Independent, of course, meaning there's no relation between the two samples. So when we do this, because we have two samples, we're going to have a population mean in one and a population mean in the other. And our null hypothesis is always going to be that they're equal. And then the alternative could be, well, maybe this one is less than that. Maybe it is greater than that. Or, of course, not equal to. So this would be a left tail test, a right tail test, and a two tail test. And we'll get that from the problem, whatever our alternative hypothesis is. So those are three choices. Okay, we know about independence. Dependent, we're not going to do that. If we had time, we would do matched pairs because that's a nice way that people do experiments. So here's our data. We've got female and male professors. They got their course ratings, and the question or claim, does there appear to be a difference in the evaluation scores? So we've got our alpha. And from here, here's my null. So let's call this population 1 and 2. So we're saying, okay, the mean of females is equal to that of males. And my alternative, in this case, does there appear to be a difference? Well, it's not saying it's less than or greater than. So are the ratings for female professors different from those of males? Okay, we're going to do a hypothesis test. We're not going to do a confidence interval. So it's just like chapter 8. So we have two samples. So here I called one the females and two the males. Samples are independent, simple random. Now, we do not have this because neither one of our samples is greater than 30, and we need both of them to be. So we're going to assume this. So when I write a problem, I always put that in there. We could do dot plots, but I'm not going to waste our time with that. Okay, here's our big formula. Now, it's not often, in this case, it is always assumed to be 0. So this is gone. We don't have to worry about that in our formula. So you can see we have the sample mean of the first population and the second, and standard deviations and sample size. So let's do our analysis. The N of females is 12. Excuse me, the N of males is 15. So we're going to use for our degrees of freedom the smaller, and that'll be 11. So what we need, because it's two-tailed test, alpha was 0.05, so we split that in half. And now I need my critical T. And we can go to the Triola formulas and see just how messed up this is. Let's see, where is T going to be? Here, I think. There we go. We have the area in one tail or two tails, same column, middle column. Degrees of freedom is 11. T is 2.201. That's the negative one. And there's the positive one. So now it's a calculator issue. We're going to do the test statistic. And the author didn't give us this information until right now. I'm going to, I did this with 3.867. I rounded a little bit to like the 3 decimal places. Now, some of you, don't forget, you may need parentheses here. And try on your calculator. I will tell you, I got a different value. I got negative 0.656 because I rounded, so I'm not quite as accurate as the author was going out to so many decimal places. So that's our T value. Remember, that's 0. So it makes it a little easier. So let's go back, make our conclusion here. We got a test statistic of negative 0.657. That falls inside. We're going to fail to reject. So the author makes their conclusion. There it is. We don't have sufficient evidence to reject the claim that female professors and male professors have the same mean course evaluation score. We could not reject this that said they had the same. We failed to reject. And so that's basically this section. I'll do some problems in class.